let's get started then with the lesson. So let's remember some stuff, right? So you have this table in front of you. And what type of normal distribution is this? It says it on the top of the table. Standard. And standard, right? So normal distribution roughly means bell curved, right? But let's see, what does standard mean? The standard part of normal distribution tells us what? Anyone remember? It should be in your very top of your notes from that day. Standard refers to what about the deviation? It's continuous. A non-standard one is continuous as well, but the normal distribution is example of continuous, correct? Unlike discrete from the last chapter. Well, that's true, but it's not what the word standard specifically refers to. Can anyone tell me? Give you a hint. Anyone? Yeah, 0 and 1, right? This is the mean, right? So this is saying that this distribution is centered over 0, and the standard deviation is 1, right? Now, you think that will be the true most of the time in real life? No, right? For example, male height and then female height, which we'll do some examples with, those are normally distributed, definitely don't have a mean of 0. What would a negative height even mean, right? So what we're going to figure out is how do you use real applications? It's like an extra step to figure out the standard stuff, right? And then 3, we'll probably not get to talking much about this, right? But this is going to talk about it, right? I have some distribution, right? I have height that is normally distributed, right? With a particular mean, right? Let's say I take, right, from the population, I take groups of 5 men, right? One group might be me, Frank, Jason, right? Jack, Leo, right? Just imagine there are a very large number, but there's a finite number of groups of 5 men, right? Of 5 men that I could choose, right? Each of those groups would have a mean height, right? And then let's say I put those means, right? Remember, this is a little weird. I'm getting a distribution, I'm finding the mean, right? Then I'm writing down all of those means on a piece of paper. Be a very long piece of paper, right? But those means themselves would have a mean, right? And those means would also have a standard deviation, which is weird. I could also take the 5 group, right? Like the one that me and Frank are in, and I could take the standard deviation of each group. And then I could put those on the list, and those would also have a mean and a standard deviation. So you have a mean of means, a standard deviation of means, right? And standard deviation of standard deviations. There's a lot going on there. We're just going to barely come into that, right? And then you might wonder why are so many things normally distributed? Well, part of it has to do with what I'm talking about there, right? But we'll get into that. So let's do the easy part. So here, a cool thing is y'all already are supposed to know how to do this. Although some of you guys didn't, right? You've just forgotten that. So remember a z-score represents the number of what away from what? Standard deviations away from the mean, right? It tells you, right? So if you z-score of 2, if your height has a z-score of 2, that means you're quite tall, right? Because you are 2 standard deviations to the right of the mean. If you have a next z-score of -2, you're a shorty, right? You are 2 to the left of the mean. Am I pointing? I'm pointing to my left, which is no wait. I point to your left. Okay, good. This is something I always have to be aware of. All right. So we did this before for norm, right? We just had the word standard normal, right? So the standard normal was nice in that your x and your z were the same thing, right? Here you have to go from x to z. Here's the key concept, right? Before, right, standard deviation 1, mean was 0, right? Notice if the standard deviation is 1 and the mean is 0, in that case, x minus 0 over 1 is equal to x. So in the standard case, it's easy. X is equal to z, right? So there's no translation. Here there is, right? So first, you're going to have x, right? I can't create a standard normal table, right? Sometimes you see this. So they don't quite use it this way, right? But like when you when you were all babies, right? We were all measured and they would say, you're in this percentile because this is your height. They were kind of having this table, but for human height at a specific age, right? You can't create a table for every distribution. So what you kind of do is you transform a non-standard normal distribution to a standard one using the z-score, right? That's the formula. And then to go from z, you go to the probability or area, right? For this, you either use the table or on your calculator, you use normal CDF, right? So this is the diagram, how you solve the problem. First, I kind of do this in a different order than they do it, right? You want to sketch your curve, right? But X you can't know on its own, so you need to change it up. So you need to convert to a z-score, right? So this is X to Z, that's what this step is. And then from Z, you want to go to P, right? Okay, so I need to take, yes. So you can try to do this whole, sitting mostly the taller, I'm mostly looking at men, and I would be surprised if has anyone ever hit their head on a shower head when they went into a shower that was unfamiliar to them? No, that's just me. Okay, maybe I'm tall, and I've been to some really like much older homes, right, that have low shower heads. So we're trying to figure out, right, if I have a shower head that's 72 inches tall, what percentage of men are taller than it and might hit their head on it? So first thing I want you to do is calculate the z-score. You can do a little bit more if you think you can, right? But at least start with that while I quickly use the restroom. All right, everyone understand what they're being asked to do here? Okay, so anybody get 1.21 for the z-score? Okay, perfect. That's not too hard, right? So notice your z-score is this, right? So in this particular case, we have, right, then you kind of have to identify it, right? Make sure you don't switch, right? I know in the first celebration we did, I've commonly found this. If you forget this formula, let's just try to intuitive it, right? So notice a man who was 72 inches tall, right? That person would be 3.4 inches taller than the mean, right? Taller than average. That difference, well, how many if a standard deviation is 2.8, how many fit in there? Well, that would be the ratio. Be 1.21, right? Approximately. Notice that this top thing is measured in inches, right? The 3.4 and the 2.8, they're both measured in inches. So Z is measured as a ratio, right? Just like, so it doesn't matter what units you use, right? And nor should it. Okay, now we have the z-score that corresponds to X. So now we just kind of have to translate this. So here we are looking for the probability that X is what? Less than 13, equal to 12. We're looking for the probability that X is, look at the sentence, probability that X is, find the percentage where X is what? Greater than 72, right? So that's step one, kind of. And we know that, okay, 72, we can't use this table, right? Because it's not in the correct, it's not translated to something that's good for your table. So this would be equivalent to, so being taller than 72 inches would be equivalent of having a z-score that is smaller or larger. What's the correct? It's also larger, right? Than right? Because that X and that Z correspond, right? So then it's not a bad idea to kind of sketch a little bit what's going on. So I'm looking for am I looking for area to the right or to the left? To the right. So that's a little bit tricky in that our table gives us area to the left, right? So I had you, those of you who had the table that are new for the first time, you might want to draw this diagram, right? Like on your table. Some that looks like, well, maybe that, right? Showing you that you're always getting area from the left, right? So in this case, since you're getting area from the left, I want to not just take the number from the table, but I want to do 1 minus the area, right? Because the table is going to find the area that's over here. So hopefully you guys can all now read the table well enough to notice that for 1.2, the corresponding value for 1.2 is point, where the first two numbers, I'll finish writing it. 8, 8. That's about 11.3%. They found 11.2. They used a slightly different table. It's all good. It doesn't matter. Now you can, well, no, we'll do that in the next one. So helpful hints, right? Draw it out. Draw out the normal distribution, right? Here it was pretty easy because we're looking like to the right of a line. If you have, by the way, I have this presentation. This time I made sure to post it ahead of time. So if you have in between two lines, it's really helpful to post it out, right? Especially remembering that our stuff is from the left. Don't confuse z-scores and areas, right? So on these tables, z-score is on the far left, right? And on the top. Areas or probabilities are in the center, right? So you want to think about, what do I have? What am I going to, right? Also, don't screw up in not finding negative z-scores, right? Before it was easy not to do this because I just gave you the z-score straight up, right? So just remember, if you're looking at something that's below average, right? Your answer should be below average, right? Also remember, just like we said, the total area under the curve is 1, right? Area has to be positive, just like a probability. So you should be getting an answer between 0 or 1, or an answer between 0 and 100 if you're writing it as a percentage. Okay. And you can kind of get a sense of it, right? If you draw it out, I'm not good at drawing the normal curve, as you probably noticed. But as long as you put both like the vertical lines or the vertical line on the correct side of the center, you can get a sense of whether the answer should be like beneath, under 50% or above 50% easily. So that can give you a sanity check when you get your final answer. Questions? All right, let's read this. The height. So pilots need to be between 64 inches and 77 inches. Right? And a standard deviation of 2.9. So we want to find out what percentage of women fulfill this height requirement that's required probably to fit in the airplane appropriately, right? So how is this problem different than the one in the previous example? How many z-scores am I going to have here? 2 as opposed to 1, right? So let's try to write this out. So x is the height. So I want to find the probability that, so let's translate each of these into z's. So you want to do, we'll make sure you're consistent. So the first x is, the smaller x is 64 or 63.7? X is 64, right? Mean. You can use just 2 decimals if you're going to use your table because there's no more than that in there, right? Okay, so now this helps us draw our diagram, right? So we're looking for the probability that Z is between. So first you translate from X's to, sorry, from X's to Z's, right? Notice even though this is a small number, it's more than 0. So it's still to the right, right, of the center. Hopefully yours can be more symmetric than mine. But this also helps us give us a sanity check. Based on this, we'd expect the number to be more or less than 50%. I did not do a good job of drawing it, but notice both vertical lines are to the right of the center. Half the area is to the right, so I should be expecting something that is less than 50%. We good with that? Do we see how I'm thinking about that? Okay, let's look at our table. Right, we subtract the area to the right, so we have the area to the left. So I don't want to subtract the area to the left of this number and then the area that's the left of this number, but we kind of have a problem. Let's look at our table. What's the problem? What? Any thought? It's correct. Any thoughts on how we might fix that? So let's see. The largest number is 3.99. What percent? So the area to the right of 3, notice for 3.99, the answer is 99997. So that is what? 3/1000 of a percent. So we're talking about 3 in 10,000 people at 4 standard deviations away. So at 4.6, roughly, we can just say that that is equal to 1, right? We can just say, right? Just imagine what would happen if this table went out. We would just have a ton of 9s, right? And then maybe like a 5 or something, right? So another way of thinking about this is such, right? This is like saying, this is, right? Remember we said the vast majority of your data is even 2 standard deviations. So when you're talking 4.5, you're really going nuts, right? So it's like saying women that are taller than, I don't know, 5'2", but are shorter, right? When I say 77 inches, I might as well be saying 30 feet, right? That's basically all women. So I can just say that this is approximately equal to, that part's 1. Or I was going to say it's approximately, I can roughly just ignore the upper limit, right? That's what I was going to say. If this number is more than 4, you can just ignore it and say that, or you could say it's 1 and subtract that way. So then we just need to find the area that is to the right of 0.1, right? So that would be 1 minus the corresponding thing for 0.1, which is, this is roughly 47% of women, right, are tall, are fit the height, are not too short, right, nor too tall to be to fly, right? You're kind of confused how he did this. Notice how far out this z-score is, right? This line's basically flat there. So we don't have a number there because we can treat it as 1, right? All women, it's not necessarily true, but what, 70 inches is 5 foot 6'5". So, right, outside of the WNBA, not finding a lot of women that are that tall, right? I don't think I've ever met a woman who was more than 5 foot. I'm sorry, 6'5". Maybe you have, but we're talking about 1 in 100,000 people, right? You're talking about that they're like the number of women, such women in Illinois would easily fit in this classroom, probably with chairs left over. questions here. So you just draw the diagram out and you figure it out, right? So notice the process we're doing. We started always with what? We got three things in here, right? We started with X, right? Then we translated X to Z, right? There's a formula that does that. And then we went to P, right? Which we used. I'll show you the other one, right? So I forgot to show this one, normal CDF, or you can use your table. That went to P, right? So the next question is, how do I go the other direction? But first, let me remind you how to use the calculator, especially if you weren't here before. So calculator is best for finding between two. So notice above vars, it says DISTR. That stands for distribution. One mistake you don't want to use is never use this top thing. You will never have to use this top thing for, I can imagine anything. I've never used it, ever. You don't need it for anything. So just go to 2. We put the lower limit, right, which is 0.1. And then this time you can kind of make it more precise, right? If I add in a third decimal, I would have gone 1.03, comma, the upper limit was 4. So we got what I did. I got 46.0. Here we got 46.9, right? Not a big deal. Not or we had 46.0. Now I have 45.9. No big difference, right? And this is what I'm saying, right? That we can basically treat that like it's 1, right? Okay, 4 standard deviations. Let's get rid of the decimal point. Is that going to be that much more, right? Now I'm letting women that are 80 feet tall. Barely changes the percentage of women that satisfy, right? Because if I put a limit on only women over, 6'5", that's pretty much right. That's my upper limit. That's almost the same as having an upper limit of 80 feet tall, right? Because there's so few women that are above that height, right? So that's what I was saying there, right? Questions. This is also how you would use it if we didn't have an upper limit for the height, just the lower limit. You could just put in some large number that's like 400, right? Or whatever. Questions. So how do we do the opposite? That's what we're talking about next, right? So instead, right, to do the opposite, you will be given some probability, right? And our goal is to figure out, right? I need a percentage, right? I want the probability. A woman is taller than X inches. I want that probability to be 10%, 5%. I want a height that only 1% of women are taller than, exactly 1%, right? These are the sorts of things. Or only 1% of women are shorter than, right? So the intermediate step, right? You're always start with X. Then with P, Z's always in the middle, right? So this step, your calculator, let's see if anyone remembers. What was the other thing we learned on the calculator? Go the opposite direction. Anyone remember it? Yeah. Yes, so that stands for inverse normal, right? Yeah. So that's INV norm for the table. Now your calculator, I'll be honest, because you'll find it out eventually. If you want to. Think for inverse normal. I know for the other one, it has a way that you can not have to find the Z values, right? But then you have to type in your X, your standard deviation, and your mean. And I never remember in what order. And I want you to find this. I'm always going to want the Z-scores anyways, right? So it's just too much to remember how to put that in your calculator, right? So if you look that up, go ahead, use it. I don't care, right? But I'm not going to teach it to you because I don't think it's good form. So this is the inverse process, right, of what we're doing. So again, you'll sketch it. But then using technology, so inverse norm, or the table, right? You are looking, if you're using a number table, right, you're no longer looking at the edge, right? Because you are looking at the body. You're looking at the body of your table, right? Because that's the percentage, because in here, right, you have the percentage of area, right, to the left. So I want to find the particular ZVAC. So I want to find the closest I can to the number in the table and then find the point there, right? So this is how, so this went from P to Z. And then to go from Z to X, I need to use this formula right here. This formula is fairly intuitive. Well, it's hard to see it until you use an example. But remember, I gave you a different formula before, right? It seems like I've given you two formulas that involve Z. But these are actually the same formula, right? Notice I can subtract U from both sides, right? Right? Then I could divide both sides by sigma. So notice this formula and this one. You memorize one, right? And you can do like just a tiny bit of algebra. You have both. These represent the same relationship, just written. It just depends on which variable we have by itself. Just like I could say, hey, the relationship is that number of hands divided by 2 is the number of people, right? I could also say number of people times 2 is the number of hands, right? You see how that's the same relationship, right? One of them necessarily implies the other one. Same thing between these two formulas, right? These are mathematically equivalent. They are both ways of expressing the same mathematical relationship that just exists, that just is. Questions here? All right, so let's do an example like this. All right, so one thing you want to, okay, this is bad because they're making it the 95 shortest percent of women. If I was designing a plane, right, so it would also accommodate most men, I would probably want to do the 95% of tallest women. This is a poorly designed problem. I've thought about change. Maybe I just need to change the story with it. I've been wanting to change this problem, but then I wouldn't have the, because it doesn't make sense, but then the accompanying graphics would be wrong, right? And it wouldn't be the problem in the book. So I don't know what to do about that. So basic, roughly just, we want a plane, right, that accommodates the shortest 95% of women, right? So what is that height limit? Basically, we want to find a height that has 95% of women shorter or equal to this height, right? So in other words, we are trying to find let's draw what we have, right? So I know it says it wants 95% of women to be shorter than that, right? So am I going to have my Z value? Is it going to be somewhere over here or somewhere to the left or somewhere to the right? Well, we're looking at the area to the left, but the Z value itself is to the right. Let me show you, because I want 95% to be on the left, right, and 5% to be on the right. So this is 95. I want this to be 5. So right now, notice I'm going from my p-value, 0.95, to my z-value, which I don't know the value for yet. Okay, so we have our table. Am I looking on the front side of my table or the back side? Oh, that's the back, right? Both are on the. Yeah, the side with the positive Z numbers, I think is what's right there. I could tell because I could see that you were holding it this side of the table, right? So here's the thing you need to be cautious about. I have the number 95 point. I have this number in my head right now, right? Is this where I want to go? I'm just shaking your head. Where am I? Should I be looking for the number 95? Everybody in the middle, right? Thank you. Right. So we won't find it exactly. I see this number is tiny bit under it. This one's a tiny bit over it, right? So like right there, that would be the sweet spot. So that would be somewhere between. So I got Z is going to be 1.645, right? Now I've done Z to P. Sorry, I did the opposite. I went from P to Z, right? The next thing is I need to actually find what? X, right? And here's the formula. X equals mu times sigma Z. This formula, try to paint, I know, like, just if I told you, they walked by, I was going to ask them what was so funny and share it with the class, but, you know, I was in college, someone just screamed down the hallway really loudly, "I'm going to Vegas." It's like, okay. All right, so 2.9, that's the size of the standard deviations, right? Remember, see, just keep remembering yourself, number standard deviations. So each standard deviation is 2.9 inches, and we got 1.645 of them, right? So to figure out that, right, multiply that together. We're adding that because we know that the z-score is positive, so that's how much taller than the average woman it would be. So then you add that to the height of the mean, the average woman, right? And that would end up giving you the height of the person that is that many standard deviations above the mean, right? So when you do that, you end up with roughly 68.5 inches, which is about 5'8.5". Any women in here taller than 5'8.5"? No. Okay, everyone gets to go. All of the women get to go on the plane. Apparently, none of the men do, though. I don't know why they chose this. This is not the best way to design a plane. All right. So the answer is, and this is, if you want to think about this, 95% of women are or shorter. So this is how we solved this. You want to do this in your calculator, same thing, inverse normal. You just do inverse normal area to the left of the z-score that you want, right? So in case you were gone on last Wednesday, second distributions, 3 inverse norm. You look at videos, I'm not sure if I put them on there. If you don't have a calculator with you or you want to use Microsoft Excel, I don't know it in Excel, I could teach it to myself, but instructions for how to do anything actually how to do in the calculator in the textbook for Excel because the word Excel is in the textbook title. Questions here? All right, so we're between sections. So I will give you, I was going to have you discuss, but we ran out. So let's just take 3 minutes. Let's be back at 3:27, right? I'm just trying to make sure that we have enough time to get as far as I did.